Hello everyone, my name is Sadia, and today I'm going to be talking about how me and my co-authors globally measured connection tampering without responsive endhosts. Many users will often want to access a domain on the internet, only to end up experiencing network interference that prevents them from doing so. And this can be due to nation-state censorship, university firewalls, and corporate intrusion detection or prevention systems. And the policies and mechanisms used for such interference can vary drastically across networks. Therefore, we must measure network interference both broadly, measuring as many networks as we can, and deeply, testing for as many domains as possible. But what makes these two goals difficult is that global interference measurement tools today rely on having something inside of the country they're studying. So for UNI, these are local in-country participants. For SensorPlanet, it's servers, and for ICLab, it's VPNs. Therefore, interference measurements are largely limited to where servers and participants are safely located and to rates that don't affect the live end host. In-country end hosts are also difficult to procure in countries and networks with small populations, low internet penetration rates, highly oppressive regimes, and poor internet infrastructure, and this leaves many networks unmeasurable. Furthermore, countries and networks that have IPv6 currently have no global network interference measurements, as the vast majority of addresses over v6 are unused. UNI is currently the only measurement platform that measures some v6 interference, but only if an UNI participant's network supports that v6 connectivity. So we present MINT, Measuring Interference with Non-Responsive Targets, a tool that conducts network interference measurements by sending probes to non-responsive IP addresses. MINT allows us to conduct broad measurements, as almost every network has non-responsive hosts, especially IPv6, and also deep measurements, as probing at higher rates doesn't really affect any live end host. MINT is the first global active network interference measurement of HTTP and HTTPS network interference without the use of any responsive end hosts. And MINT's technique can be used to measure both IPv4 and IPv6 interference and is the first tool to measure v6 interference at scale. Because MINT requires these non-responsive unused IP addresses, it's especially effective with v6 because such addresses are plentiful. So MINT builds off two earlier studies that use the same technique, TMC in Turkmenistan and GFWeb in China, but both only measured their specific countries and only over IPv4. MINT, on the other hand, can virtually measure every country or network that has a non-responsive IP address and can measure over both v4 and v6 networks. So MINT measures network interference by sending probes to non-responsive targets, IP addresses that have no live machines behind them. But in order to be successful in measuring interference without end hosts, MINT relies on three key features of networks, the first of which is called bidirectional interference. And this is essentially when the middle box is agnostic to whether or not the client or the server is inside of the network that is deploying the network interference. We measured the prevalence of bidirectional interference and found that essentially every country has some level of it. So bidirectional interference means we can initiate measurements from outside the country of study, but we need something else to make sure we don't need any help from the inside. MINT needs the middle boxes it's measuring to not follow the TCP protocol exactly. And fortunately, this isn't too uncommon. In particular, if the middle box fails to see a proper TCP three-way handshake that's supposed to precede some sensitive request, we need that middle box to still act as if the handshake happened and end up tampering the connection anyway. Instead of simply removing the handshake altogether, though, we discuss in the paper 6 different packet sequences we can send that trick these middle boxes into tampering, even though with these packet sequences, we don't get any packets back from hosts within the countries of study. So we tested various packet sequences against v4 and v6 prefixes and discovered that about 8.5% of these /24s showed TCP noncompliance, which might sound small, but it's actually around 15 million prefixes. And for v6, it was even higher at 33% of these /48s. So now these packet sequences can be sent to non-responsive IP addresses, thereby removing the need for end hosts. And this reduces ethical concerns as we no longer have to worry about any in-country participant or machine as the endhost, and is also applicable in more networks as more than 90% of all /24 prefixes and 100% of all /48 prefixes we probed had a non-responsive IP. And finally, this allows us to test millions of domains, as higher scan rates won't affect any live endhost. So Mint's scanning methodology takes a two-step approach. The first step involves finding non-responsive hosts. So we essentially just conduct a ZMAP TCP SYN scan over all these /24 prefixes and active /48 prefixes collected from hosting NTP servers. And we omit any IP addresses that respond to our probes, leaving us with only the non-responsive ones. And to these non-responsive IPs, we send custom ZMAP packet sequence probes utilizing 460 domains and 6 different packet sequences for our final scan. And we repeat this entire process twice, once for HTTP and once for HTTPS. So after our scan, we wanted to determine where Mint was successful in triggering network interference. This map shows the number of /24s where we triggered interference relative to the total number of prefixes we probed over HTTP IPv4. We were able to measure more than 75% of these /24 prefixes in many countries, including Yemen, China, and Uzbekistan. This next map is for HTTP IPv6 and shows the number of /48s where we triggered interference. And again, this is relative to the total number of prefixes we probed. And so we're able to trigger interference in greater than 90% of the prefixes we probed in China, Uzbekistan, and Jordan. We also wanted to see how Mint compares to previous tools. So here we compare Mint and SensorPlanet. And this plot doesn't really show how many networks or ASs Mint and SensorPlanet can measure, since Mint can measure interference in any network with a non-responsive IP. Instead, it shows the ASs and networks where both can actually trigger positive examples of network interference. So Mint is able to measure 6,348 more ASs over HTTP IPv4 than SensorPlanet, though I do want to point out that there are still some ASs that only SensorPlanet can reach, which we discuss more about in our paper. So next, we compare Mint and UNI. And again, this is the number of ASs and networks that Mint and UNI can trigger positive examples of network interference in, but this is over HTTP IPv6 this time. So UNI is able to measure 931 more ASs than Mint over HTTP IPv6, but this may be because UNI's in-country participants are able to cover more IPv6 prefixes than the active /48 prefixes we collected from NTP servers. Nonetheless, Mint can still scan these ASs more broadly than UNI, as UNI's in-country participants can only test a few domains per AS. Because Mint is able to measure network interference more broadly and deeply than previous tools, it actually enables studies that were not possible before. And one of these studies is quantifying the level of centralization of interference mechanisms for different countries. So we essentially calculated the coefficient of variance, or the COV, of packet sequences that trigger interference and plotted them together. And a lower COV here means interference is triggered by similar packet sequences, suggesting a centralized system, while a higher COV means more variation, pointing to decentralization. For example, countries like Turkmenistan, known for centralized control, have a lower COV on this plot, while countries like the US, with more decentralized interference, show a higher COV. We can also determine the level of centralization of network interference policies for different countries. And essentially, we apply the same idea as before, but to domains instead of packet sequences. So a lower COV here means networks block the same set of domains, indicating a more centralized interference policy, and a higher COV here denotes a more decentralized interference policy, as networks interfere with a wider variety of domains. So these results mirror those for the infrastructure centralization. Countries like Turkmenistan show centralized blocking policy, while countries like the US display more diverse decentralized policies. In our paper, you can also find more results, including which countries and networks interfere with traffic bidirectionally, case studies over ASs that deploy IPv4 and IPv6 censorship differently, how to identify IPv6 residual censorship in China and its subsequent circumvention, and more results for all combinations of protocols. With Mint, we're able to actively measure global network interference without any endhosts. Mint enables us to finally measure IPv6 tampering at scale and lets us answer questions that weren't possible before, like measuring how centralized interference infrastructure and policy are within specific countries. Feel free to learn more about Mint in our paper, and we also make our code publicly available on our website.